So today's speaker is Dhrubaditya, and he's a good friend. I know him for quite some time. He did his PhD from ISC, then he went to Nice, and then he moved to, after several more research positions, then he is right now in Nordic. He's been working here for quite some time. And his research interests are varied. He works in turbulence, particles, some clouds as well. And now today is going to talk about, in a broad topic of postmodern turbulence. I look forward to hearing you, Dhruva. Okay, so please take over and start your seminar.
Thanks for the nice introduction. I have always liked visiting Kanpur, and I wish I could have been in Kanpur right now. It's still not too warm, I guess. But thanks anyway for inviting me. I will talk about something which is not really, could be turbulence, but this is not what traditionally turbulence is. What I am calling postmodern turbulence. So if you kind of have some idea of what postmodernism is, which I don't, it seems that people say postmodernism is one way of postmodernism. Postmodern art, for example, is to look for art where things were not considered domain of art traditionally. So like a garbage dump, and to find some art there. So to look for art where there is not art traditionally, and the postmodern turbulence is to look for turbulence where turbulence has not been found traditionally. And what is the regime where you expect turbulence least? So that is the regime where you have the Reynolds number to be extremely small. So I think to this audience, I don't need to explain what Reynolds number is. The Reynolds number is a ratio of velocity multiplied by length divided by the viscosity. The Reynolds number being small or zero basically means that the viscosity is extremely large. Those are the cases where you don't have any turbulence, but these are important physical problems. For example, one of them is the microfluidics, where you have extremely thin micrometer width channels and you have liquids flowing through them. And this can be used as a lab on a chip. Practically a whole biology or chemistry experiment can be brought down on a microscope slide. These are one domain where zero Reynolds number is important, or very small Reynolds number is important. Another one is swimming microorganisms. For example, over here, there is a picture of swimming bull sperms, and how they move, how they swim, and if there are many of them, how will they start the flow? That goes into the domain of active matter. And all of these are extremely topical problems. But there are certain difficulties in this field, which is traditionally very well known. And I will use a video to remind you of them. This is a video which was made by the National Science Foundation quite a long time back. And the person in the video is Da G.I. Taylor. If you haven't seen this video before, you should. This is in YouTube.
There are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space, I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion. To see what happens, we have a second apparatus that is filled with syrup. It has a wider gap, and we can look down on it. A little colored syrup is injected to mark the fluid. When the cylinder is turned, this fluid is stretched round the annulus. Now the inner cylinder is turned back exactly to its starting position.
So if there is anything that is not turbulent, it is this. And there are some important lessons I want you to remember from this. One is that the flow is instantly determined by the boundary, and there is no mixing. What looks like mixing is actually not mixing. Things are time reversible. You go forward in time, you come backward, you see exactly where you started with. So in a domain like this, I am now going to look for
Can I
turbulence.
make a comment, Dhruva, in this? So it's okay. I mean, I agree completely with G.I. Taylor and you as well, but I want to make a remark. It is not time reversal because there's a viscosity in it. If you look at small scales which are not visible with the naked eye, there is diffusion. There's molecular diffusion.
There is molecular diffusion, yes.
So it is not because in fact it's a viscous flow. There is a dissipation, and it is not a time reversal symmetric. It's just that it is not turbulent diffusion. So I cannot really call it a time reversal symmetric because this is not because of viscosity there will not be time reversal symmetric.
This is an interesting comment. This is I believe this is a really interesting comment. But let me sidestep it at the moment. This will take a long discussion.
So yeah, we'll discuss it at the end of the talk. Yes.
Mahendra, I agree with you. This is a really interesting comment. Yes.
Okay, great.
Anything else?
Nothing else. So let's continue. We'll come back to it. Yeah.
Which is, please feel free to stop me and ask questions. I get bored just looking at a screen and talking myself. Okay, so please stop me whenever you want. Okay, so now we have looked at something which was very simple because there were no nonlinearities. See, the Navier-Stokes equation has nonlinearities, but when the Reynolds number is 0 or small, the role of the nonlinearities are minimal. So how can we introduce nonlinearity in this problem or similar problems? The question is almost perverse because normally we physicists hate nonlinearities. What we want is to get rid of nonlinearities. But you see, nonlinearities play the other very important role of mixing. And in a microfluidic, for example, when you want a chemical reaction to happen, you want two chemical reactants to mix. And this is an extremely slow process in a microfluidic device. So if we could make that faster, that would be a really significant advancement in this part of science. So instead of Euler equation, which brings the nonlinearity in fluids, we are now going to look at something called Euler buckling. And again, I will show the same movie of G.I. Taylor, but a little bit later. So here he puts a small thread in the same flow. So
the motion carries the body around and also makes it rotate. On reversing, the rigid body returns to its original position and orientation. If, however, a flexible body, like this bit of yarn, is inserted, the reversal of stress will alter the shape of the body so that it will not return to its original position. In the next experiment.
Okay. So you see, the important thing is, there are two important things. One, with G.I. Taylor already said, the thread doesn't come back to its original position, but also it doesn't come back to its original shape. It comes back to a very different shape. It looks buckled. And this is the very old problem of Euler buckling, where you think of a filament. So let's say something like this, and you give two forces from two sides and it buckles. Okay, this is what a buckling is. So when you put this in a flow and say it moves with the flow, then if the flow pushes it from the two ends, it is going to buckle if the flow is strong enough and the thread is going to be soft enough. Now, it can buckle at different time in different directions. So if it buckles in all the very possible directions, one thing that can happen is it can never repeat itself. If it never repeats itself, it's going to be a very efficient mixture, which is what we want in this case. So this is the real motivation of looking at this problem. So how do I go to the next slide? Okay. So now I am going to talk about a numerical experiment, which is very similar to the actual experiment that G.I. Taylor showed you. But instead of a Taylor-Couette flow, which are two concentric cylinders, I am going to think of a plain Couette flow. So I am going to put a thread, which is here at time t equal to 0, vertically downward. Vertically downward is my y-axis. And I am going to put it in a flow that is only along the x direction. And the flow is a linear shear flow. It's the x component of the flow increases with y. So you have this kind of a structure. At the same time, the flow is periodic in time. So the velocity u has a sine omega t in it. So you see in one part of the flow, the thread is rotated in one direction and stretched. But in our model, the thread is inextensible. So it doesn't actually stretch, it does just rotate. And when the flow comes back, you see this structure developing in the thread. This is what buckling is. We are modeling this by solving this set of differential equations, and let me describe them to you. So every point of this thread is approximated by a small sphere. And for each of those spheres, you could write an equation of motion, and there will be two terms in it. One term, so to start with equation of motion, you will just write the Newton's equation. So of course, there is mass times acceleration. Let's not worry about that at the moment. And then on the other side are the forces. So there will be one set of forces because of the elastic Hamiltonian. I am not specifying here exactly what the Hamiltonian is. That will come a little bit later. But whatever the forces are, they are gradients of the elastic Hamiltonian. These are elastic forces and reversible forces. Then there will be other forces because this thread is moving in a viscous liquid. And those forces are proportional to the velocity of the points, and they are actually here. So this is the velocity of every point multiplied by something like 1 over mij. And finally, there will be another term, which will be the velocity of the flow at that point. Once you reach there, you will identify it with the limit where you take the limit of very high dissipation. As you know, by studying highly dissipative harmonic oscillator, in the limit of very high dissipation, the mass term, the second derivative in time from the equation will drop off. Once that happens, your velocity, whatever was multiplying the velocity, you invert that matrix. You will obtain an equation like this, where this matrix M alpha beta ij is a matrix that gives you interaction between ith and jth bead because of the flow. So if you are thinking of a very simple problem where every bead is like a Stokes sphere, then this term, this matrix will just be a diagonal matrix. But that will not be proper because of the flow, because of the liquid, if I move one bead, every other bead is going to know that. And how are they going to know? They are going to know it as a solution of the Stokes equation. So it is actually the solution of Stokes equation that goes into building this MIJ matrix. It has alpha and beta, which are the space part, and ij, which is the ith bit and the jth bit. Altogether, this is the equation. And you can see that this is a first order equation in time. Okay. So there is a diagonal term for I equal to j, which comes just from the viscosity. I mean the local viscosity. And there is an off diagonal term, which tells you that if I move one bead, another bead knows about that. So this is the non-local viscous interaction. And I solve n such beads in numerics. And then I find out what happens. So what happens is actually quite interesting. So see, in this problem, I am putting a shear and then going back, and then putting a shear and then going back and forth. So my external flow is going to come back to exactly its previous state, initial state, after a time capital T. So I can say that let me look at the whole system with snapshots of capital T. This is something I am going to call stroboscopic viewing. So, and now I am going to look at threads that are softer and softer. For a thread that is quite stiff, which is the case here, you find that after certain number of times, certain number of going back and forth, it develops a buckle state and it stays in that buckle shape. So the thread, which is this one, okay, so gets rotated and then comes back buckled and then gets rotated and then comes back buckled and then gets rotated and then comes back buckled in exactly the same way every time. So if you look at the system after time capital T, you will see exactly the same behavior. Let's say T equal to 12T and T equal to 16T, they look exactly the same. When it becomes somewhat softer, then things start getting more interesting. So that is the case B here. You can see this at 4T, it has taken a buckle shape. At 5T, it is another buckle shape, which is really the mirror image of that. At 6T, the shape of 4T is back. And at 7T, the shape of 5T is back. So what you have seen is a two-period bifurcation. Once you go even softer, you get into a stage where it never seems to repeat itself. Now, there are two different subclasses in this. One is the C, where it never seems to repeat itself. And the other is the D, where if you just look at integer t, at late time, it seems to come back to its shape, but not at intermediate times. For example, if you look at 55.7t and 65.7t, you see the things you see over here are not exactly the same. So it is not really repeating itself. And finally, when the thread becomes really very soft, then for a long time, something like 60t, you see all this complex behavior. But at very late time, it seems to settle down to one fixed shape. Actually, that shape is not exactly that shape. It shifts slightly, but it only shifts from its shape in time algebraically. So I'm going to ignore that for the moment. So these are roughly 4 different kinds of dynamical behavior that you see, in addition to one, the most boring one, where the thread is so stiff that it doesn't even get buckled. Now, what are the parameters that I can vary in this problem? I can vary the elasticity, I can vary the softness of the thread, the length of the thread, and so on. So a whole bunch of them come together to give me one dimensionless number. And then there is another dimensionless number, which is the time scale that is coming from the rate of strain and the time scale that is the periodicity of the rate of strain. I put them together, and I get 2 dimensionless parameter. One is the ratio of 2 time scales, which is sigma, and the other is mu bar, which is called the elastoviscous parameter. So the bending rigidity is in the denominator, the viscosity in the numerator, and so on. And so this parameter, the elastoviscous parameter, which we are going to call mu bar, that is what it is conventionally called, it increases as the bending rigidity decreases. So as the thread becomes softer and softer, mu bar increases further and further. So Vipin, who is the one who has actually worked on this problem, has done a lot of simulation and collected them all together in this phase diagram. And let's have a look at it. So if you are in small mu bar and not very small sigma, then you see the straight phase. Basically nothing happens. The thread rotates and comes back. Then let's stick to 1 sigma, let's say sigma equal to 1.5, and go along this line. Some point it gets buckled. And some point after buckling, it gets into one of these complex phases. And then going along the same line, it goes into the complex transients. If we go along another line, which is this one, which is at sigma equal to 1, first there is the straight, then we get into the 2 period, and then we get into the complex one, and there is a large overlap between the complex and the complex transients. So it is not exceptional that the complex and complex transient, the line dividing them is not very clear. This happens in a lot of dynamical phase transition problems. And this may suggest that there are fractal boundaries in these, but those we haven't investigated in detail and we are not going to go into. So the main message from this here is that there is quite a bit of lot of different things happening. But the most interesting part of the phase diagram is this complex phase. That is where the thread never repeats itself. So that's what we are going to do, going to look at it quite some detail. So what happens in the complex phase? So you see, there is another way of looking. So in B and D, you see, I'm just plotting the thread. Okay, and they are quite complicated, and one on top of, different times are not the same. This is quite a complicated shape, and indeed we could call it complex. But now let us also look at it in another way. One way to completely describe this thread, its shape, for example, is to describe how its curvature depends on the arc length. So start from one end and then calculate curvature and plot it as a function of the arc length as you go to the other end. As both the two ends are free, they have a boundary condition that curvature must be 0 at those two ends. So here is one such plot of curvature at different times. You can see that the curvature goes up and down. It's large in the middle. It changes sign, and it's quite complicated. So for the rest of this talk, we will not think so much about where these threads are placed in 3D, but we will look at the shape, which is determined by curvature as a function of S. And the complexity of this shape as a function of space and time is something you could call shape turbulence. So that is one way of looking at the problem. You could do something else. So when the thread moves, it of course changes the flow. So now there are two parts of the flow. One is the background flow, and other is the disturbance in the background flow because of the movement of the thread. So we take the background flow out, sit at one point, and look at the disturbance in the flow because of the thread. This, you see the disturbance in the flow at one point, the velocity will have 3 components, Vx, Vy, and Vz. So here I am plotting Vx versus Vy, and here I am plotting Vy versus Vz. The orange line corresponds to the case where the thread is rigid. So this shows that this is a nice structure. They are basically, if you follow it, it goes along and then comes back in its own trajectory. So this shows that it is a periodic behavior. But you see how this periodic behavior gets spoiled into a chaotic-like structure when in the complex phase. So this again suggests that you have spatiotemporal chaos in this problem. So it is this spatiotemporal chaos that we are going to study much more carefully. So those of you who have kind of spent some time solving differential equations, particularly chaotic ones. So you know that a chaotic problem has sensitive dependence on initial condition. So you can imagine that if you solve such a problem over a very large time, maybe you are actually going far away from your actual solution and landing up somewhere else. So using differential equations and evolving them to study a chaotic problem is somewhat risky. So we will take a different approach for the same problem. And I'm going to describe that now. To do that, we will convert this time-dependent problem into a map in the following way. First, notice that the time-dependent problem, which is given here, has an explicit time-dependent velocity. This is the sine omega t in the velocity. This is explicitly time-dependent, which makes it a non-autonomous system. And as you know, non-autonomous systems are not something we like dealing with. But if I integrate it over one time period and look at what the curvature as a function of arc length look like from t equal to 0 to t equal to capital T, then I can think of it as a map. So this is the curvature map that I am describing here. So first you do is you think of curvature as a function of arc length. If you do that, from there you can find the position of the beads in 2D. This is uniquely determined if the position of the first two beads are specified. Once we have that, we use our differential equation solver to integrate over exactly one period. See, the complaint that I was making that I have to integrate over a very long time is not valid when I'm integrating over just one period. And I can keep my errors extremely low, numerical errors. So after one period, I again get the position of the bead, and then I use the inverse of the transformation that I used in step 2. And from the bead, I go to the curvature. Okay, so all of this together makes this map F, which maps the curvature as a function of S at t equal to 0 to curvature as a function of S at the end of one period. So if I now operate this map p times, I will basically see the same behavior after p actions of the map. And you can ask, what are the fixed points and the periodic orbits of this map? So if you think of a pth periodic orbit of this map, that will be the fixed point of the pth iteration of the map. So to study this, I can define the following. I operate this map p times over curvature. Then if the curvature itself, then it's a fixed point of p iterations of the map. And this is an operator I call NP. So fixed point of the periodic orbits of the map are given as solution of this equation, NP over kappa equal to 0. And for p equal to 1, these are the fixed points. For p equal to 2, 3, and 4, there are different order periodic orbits. Is that clear? Any questions? Okay. So let me go ahead. So how do we solve this? How do we find the solutions in a numerical manner? So to do this, we use the Newton's method, and I believe all the students here knows the Newton's method, but let me just repeat it once. So this is an animation that I have taken from the Wikipedia. So let's say there is this curve y as a function of x, and I want to know where it crosses the x-axis, which is the solution of fx equal to 0. So how is that solved? You first make a guess, x1, find fx1, take the slope, go to the next guess, find fx2, take the slope, go to the next guess, x3 slope, next guess. And if you keep on repeating this, you are getting closer and closer to the solution that you are looking for. So choose a point, calculate fx. If it is 0, you already know the solution. If it is not, then find the slope, follow the slope to the next approximation, rinse and repeat. That's what Newton's method is, or this is actually called Newton-Raphson. How are we going to use this for our problem? So for this, I strongly suggest this book, Numerical Linear Algebra by Trefethen and David Bow. It's a beautiful book and taught us a lot. So I'm going to spend some time describing this here. Mahendra, I still have about 20 minutes, right?
Longer, you have around 25.
Okay.
Or even longer, 25. You just take 25.
I will go slow. Okay. So what is the difficulty here? That is not the case in usual Newton's method. The first difficulty is that we are in very large dimension. So what is the dimension? See, this is a map of curvature as a function of S. So this is an n, capital N dimensional map where n is the number of beads in the thread. So it is something like 256. So it is a map in 256 dimensional space, a map of 256 dimensional space onto itself. And that's where we are looking for a solution. So when you look for a slope in such a large dimensional space, instead of a simple derivative, what you have is a Jacobian matrix. So let me explain that over here. So remember, in the Newton's method, you are at a point x0 and you want to calculate what is the next approximation where you are going to go to look for the root. So what you do is you calculate the slope, which is df dx at x0. And you say the amount I have to move delta x by fx0. This is actually the df dx with a minus sign. So then from this, if I know fx0, I know df dx at x equal to 0, then delta x, the step I need to take, is fx0 multiplied by df dx at x equal to 0. And the new guess of the solution is x0 plus delta x. So to write it in a slightly different form, you see this df dx times delta x, which is given by minus fx0. In higher dimension now, what I am doing is the following. So let's look at the flow chart here. I want to find a solution of kappa as a function of s. So first I guess some kappa, okay, at t equal to 0. And then corresponding to that kappa, I find out the position of the bead by this map K inverse. Once I have the position of the bead, I use my evolution code to evolve this system from t equal to 0 to t equal to pt, where I'm looking for an orbit of order p, a p periodic orbit. Okay. So then I use the dynamical equations to solve this and get y at pt. Once I have y at pt, I use the inverse of the K map to find the curvature again. So this is the curvature map that I was talking about before. So then from this curvature map, I can calculate NP of the curvature, and let's call that G. This is curvature at pt minus curvature at 0. So if this quantity is 0, then of course we have found a periodic orbit. Then my guess that I started with is the periodic orbit. But numerically, of course, nothing is 0. So I calculate, this is a vector, the difference of two vectors in n-dimensional space. So I calculate this second norm and then choose some error value compared to some tolerance. I calculate the error and I say, is it less than the tolerance or more than the tolerance? If it is less than the tolerance, then a solution has been found. If it is not, then I have to find out how to change the curvature to go to the next guess. And this is where the Newton's method comes. So what I described to you before is that in one dimension in Newton's method, the step you need to take is the value of the function at x0 multiplied by the derivative at, value of the function at x0 is equal to the step you need to take multiplied by the derivative of the function at x0. So now the derivative has become a matrix, which is the Jacobian matrix. And the delta x has become a vector, which is the delta k. So Jacobian dotted with delta k gives me this part, which is the fx, which is the equivalent of fx naught, which is the operator np operating over the curvature kappa. So this is the equation that I need to solve for delta kappa. Now, this is a difficult task because how do I calculate the Jacobian in a such large dimensional space? And then I have to invert it. So there are methods which are typically goes by various kind of Arnoldi methods, where you solve the same problem without ever actually constructing the matrix J. Okay. And it's not a good idea to go into great detail of this now. It will take several classes. But look at this book or look up what are called Newton or Nordic methods. There are packages which will help you solve this. One of them is GMRES. So we use that and we find solutions. But you remember the fact that tolerance is an important quantity here. If you set your tolerance too high, you will never find any solution because numerically nothing will converge completely to zero. On the other hand, if you set your tolerance too large, everything will look a solution. So there is a tricky part there, but I will come back to that. Okay. So what happens when I calculate the fixed point and the periodic orbits in this manner? So now I am plotting two things. One are the fixed point and the periodic orbit that I obtain from the picture of the map. And the other is the behavior that I obtain by solving the differential equation for a long time. The top line is one line in the phase diagram that I showed you, one line which is horizontal. So over this line, over this line, sigma is constant and mu bar is varying. First you have so mu bar is written here in the unit of 10 to the 6. First you have 0.17, which is the straight solution. Corresponding to that, the map also gives exactly a straight solution. Then you go to 0.33, and there also it's a straight solution for the evolution code. For the map, you find out that there are actually two solutions. One is a straight solution, and the other is a solution that is buckled. So now you may ask which of those solutions are going to appear. That will, of course, depend on two things. One is the stability of the solution, and other is what initial condition did you start with. So I don't know which one is working for us here, but it is, I mean, it's natural that there are all those two solutions, and maybe there are even more solutions. Only one is realized when I am looking at it in a dynamics in evolution problem. Then I increase my mu bar a little bit further. I go to 0.45. Now we don't have a simulation of the map in exactly 0.45. We have something at 0.56, which is in the same range. And what we see here is there are actually two solutions. One is a 2-period solution, the other is a 4-period solution. Importantly, this unambiguously proves that we have a 2-period bifurcation problem in this case. Now, then we increase the mu bar further, we get to 0.67. Then the 4th period has disappeared and become a 2-period, and the 2-period remains. If you go further, you come to 0.84, and actually this time there is only one 2-periodic solution. And now I keep going higher and higher. These are the complex and the complex transient phases, and there are lots and lots of complex solutions that appear here. This again provides evidence that we are looking at a spatio-temporally chaotic problem. So to remind you what is happening here, the flow nonlinearities are explicitly zero. So this has nothing to do with the usual way chaos or turbulence appears in flow equations, but it is the nonlinearities of elasticity, nonlinearities of small deformable threads, nonlinearities of filaments that are playing a role here to give rise to complex behavior. So what about mixing then? So you see the thread is in 2D. So here we have introduced a set of passive tracers in a plane just above the thread. Okay. And we have colored them according to their distance from the center. So the ones that are further away are colored in red, and the ones that are very close to the center are colored in blue. So now this is the t equal to 0. The thread goes forward, thread comes back, thread goes forward, thread comes back. Now, of course, these circles get disturbed and they come back. Now, if the problem was just like what G.I. Taylor described, that it goes forward and comes back, then all these stressor particles should also come back to exactly the position they started with. This is not what happens. So after certain time, after 8 periods here, you see that outer layers have started breaking, but the inner layers have broken down quite a lot more. And after quite a large number of going forward and coming back, things are really thoroughly mixed. So this is qualitative evidence that there is mixing in this problem. And now we are going to talk about this more quantitatively. So let's think of the kth particle among all those particles. So the Lagrangian vector, which gives the position of this kth particle, is capital X, k. And I'm looking at a time which is j plus 1 t, and looking at what is the displacement from jt. Simply put, it's the following. So I'm going to change this background flow, right? I'm going to start at some point, go and come back, and this whole change is going to be over one time capital T. So before I started changing the flow, the position of this tracer, kth tracer, was xk. I go and come back, and time has passed by exactly one capital T, and now it is xk, but j plus 1 t. So the displacement of this tracer is what I call delta x, j because j is the period I started with, and k because k is the particle I am looking at. So what is the total displacement of all the particles? I'm sorry, no. What is the total displacement of one particle after p such going back and forth? So that will be a sum of delta x, j, because and j going over 10 to p. So there are, initially I don't look at what happens for first 10 going back and forth, and then I start. And then I go for p going back and forth, and I sum over all the displacement. So the particle, say, one place moves a little bit, then 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 little bit, and all those little pieces are added up vectorially. And this is the total displacement of the kth particle after p number of going back and forth, after p periods. This is what we call rho, which is a vector, k as a function of p. Then we calculate its modulus. So the total displacement of the vector and its modulus, and then we sum over all the np's and divide by np. So that's basically the average. So this is the average distance traversed by particles. And if it is mixing, then it is like diffusion. And if it is diffusion, then this should be proportional to p. So one of the classic papers in this, where you basically say how random movement gives rise to diffusion, is G.I. Taylor's famous paper, Diffusion by Continuous Movement. You should look at that. However, that's not what we are going to discuss now. I am just going to say that this line, if it had been proportional to p, that would have been diffusion. What we see is that our data is more closer to p square. So it is actually mixing even faster than diffusion. So could it be super diffusion? Is this what is happening here is something like Levy walk? The short answer is no. And the long answer is we see it in the following way. So one of the conditions of Levy walk is that, you see, the total displacement, the quantity whose square we are looking at, is a sum of many small pieces. Each of those pieces are taken from some probability distribution. If you assume that each piece is independent of every other piece, this is a sum of independent, identically distributed random numbers. So such a thing must always behave like diffusion just by the central limit theorem, unless the second moment of the distribution that you are choosing things from is not defined. So if the second moment is not defined, then what should the PDF look like? So then the tail of the PDF should fall off slower than -2 or something smaller. Okay, it should be slow enough. So that basically means -2 or -1. I think -1, because otherwise it will diverge as log. Yes. And that basically means if you integrate that, its cumulative PDF would go as -2. Okay. Now, why talk about the cumulative PDF at all? Because if you have worked with calculating probability distribution from numerics, you know that one of the things you do is histogram. And the histogram will actually introduce some errors in your plot. And it will be very difficult to find out what the tail looks like, because there is very little data in the tail by definition. So one of the ways of dealing with this is to not look at the PDF at all, but look at the cumulative PDF, which you plot in what is called rank order manner. There is no histogram here. And what we get is a slope of -3. So that basically means the actual PDF had a slope of -4. Because you see the cumulative PDF is the integral of the PDF. And if the actual quantity had a slope of -4, its integral will have a slope of -3. So this is very different from what we expect from a Levy walk. A Levy walk would fall off much slower. So clearly this is not Levy walk. It would go into Brownian behavior, but because it is a power law behavior, the convergence to the Brownian behavior is extremely slow. Okay. So before I got into more detail, I hope I have convinced you of the following things. So here we have a situation where we are solving purely the Stokes equation. The fluid nonlinearities are exactly 0. And we have a situation that is reasonably simple. We have just a time-dependent external flow in the problem. And what is giving me here is a complex spatiotemporal shapes and also mixing of passive scalars. This is suggesting that it may be possible that we are actually have some handle on what could be a microfluidic mixer. Now, one would of course like to understand this from analytical methods. Now, there are two difficulties in making an analytical theory of this problem. One is the nonlinearity, and of course, nonlinearities are always a problem. But the second is also the non-locality of the problem because of the non-local viscosity tensor. So we ask the following question. If we throw away the non-local viscosity tensor and replace it only by a local behavior like this here, what will happen to the problem? Now you might say this problem will not remain physical. Well, let's see what happens. We again make a phase diagram, and it's quite a complex phase diagram now still. But what you see here is the complex phase is there, like these points, and the complex transient phase is also there. They are not at exactly the same parameter range as it was when you had non-local viscosity. They are somewhere else. But qualitatively, it's a similar phase diagram. So this gives us the first idea that it is possible to be able to handle this in an analytical theory. But this is what comes out for the local drag from the evolution equation. Let's just look at it. What happens if we use the maps to understand the same problem? Then some interesting things happen. For example, we see that one advantage of this local drag is that the numerical problem is also much simpler now. And then this numerical problem can now be integrated over very large time very quickly. Once we do that, we start seeing from the map very long orbits. For example, these 4 pictures here shows you an orbit which has 100t. So at this moment, I would like to pause and think how hard Vipin has worked to find a periodic orbit that has such a long time period. So let me demonstrate that to you. Not how hard he worked, but what it looks like. So this blue plot here is curvature as a function of S at t equal to 0. The orange is the same quantity after 25t. Okay, so it has changed. Here it is the same quantity after 50t. It is changed to something else. And then here it is after 75t. And at 100t, it comes back to its original shape. It's a really extremely long period. Now, if you remember your chaos courses, you should be asking me now about what happens to 3 period, right? Because we are accustomed to this very old and remarkable result that period 3 implies chaos. So are there 3 period solutions in this problem? So now I would tentatively like to claim there is, and I would like to show you some evidence for it. So here are 3 different times. So first, this blue is at t equal to 0, and this orange is at t equal to 1. Then this is at t equal to twice t, and this is at t equal to thrice t. Now you may say, look, are there really 3 solutions or are there 2 solutions? Because 2 of them looks extremely similar. So let me show you to this in better resolution. So the 3 solutions that I am plotting here are these. I am plotting them one on top of each other. There is a red solution and there is a green solution, and they are clearly different. So these two looks like a 2-period solution, but there is also an orange one. And the orange one is very close to the green one, but there are some differences that you can see over here and over there. So are these differences really there, or are these just because we have set our tolerance too high? This is something we are still figuring out. But one way to look at the same quantity is to, for example, look at the distance in the curvature space. So for every, so let's say I look at the, say the red solution, and I subtract out the curvature as a function of S of the red solution from 3 other solutions. So when I subtract the red from the red, I get 0. And then when I subtract the red from, so then I get another one where the difference is small, and then I get another one where the difference is quite large. So you see, this 3 behavior is completely repeating. This is giving quite a good evidence that we actually have a 3-period here. Although I am, maybe on even days it is a 3-period. We will worry about odd days later. Okay, so with that, I'm coming to the end of it. I will now give you a background of what has been done in similar problems before. As you can imagine, the problem of mixing at small Reynolds number is a very exciting problem. A lot of people have worked on it. So one of the early, well, there are many early papers from G.I. Taylor even. So there are some ideas where you take a microfluidic channel and you put some ridges below, and these ridges are not perpendicular to the boundaries, but they make an angle. And this paper in Science, where they did both numerics and simulations of this, what they show is that the length of the channel now doesn't need to be very long, but it is still quite long. There is another paper published in 2005 where they did the following. So here they have a highly viscous liquid and they have put lots of colloidal particles there. And what they do is exactly what we do. They have a shear that is periodic in time. So for every particle, the displacement at the end of n number of cycles is shown by this vector, and the trajectory of the particles are shown here. Again, they calculate mean square displacement, and they find out that the mean square displacement goes linearly with time, which is a signature of mixing. But this is different from our case. Here, the mixing clearly is an effect of interaction between many particles. In our case, in the first problem, we have interaction between many particles and we have elastic nonlinearity. But in the second part, I described you something which only has the elastic nonlinearity, and we see chaotic solutions there too. Now, here is an example of a famous paper by Groisman and Steinberg, which is the first introduction to elastic turbulence, where you have lots of polymers, extendable polymers, in a very thin channel, which is at small Reynolds number, not 0 Reynolds number, but small. And here is what happens when you put a passive scalar in that flow. You see that the passive scalar actually diffuses. So you see this is plotted in log lean. So straight lines are basically Gaussian distribution. And you see exactly what you would expect in Gaussian diffusion, which is that the distribution is spreading. Compared to this, in our calculations, there are not many polymers. There is just exactly one long polymer, and that's enough. Now, the polymers in low Reynolds number flows have also been studied quite a lot. The buckling is, there is one paper in Physics of Fluid in 2012, which is a very interesting paper to study buckling. What they have is a flow like this with a boundary below and a thread or a filament that is standing vertically up. So as you change the parameters of the flow, this filament can buckle. Here is another paper from PNAS in 2018, where they actually So in this paper, the thread or the filament is first placed horizontally. Then you have the strain, and the strain is going back and forth in this plane. And depending on the softness of the thread, many things can happen. For a rigid thread, you just see a rotation. See, the thread was horizontal, it rotates and gets back to the horizontal case, and that's where it stays. For a thread which is slightly softer, you then see a more complex behavior. And for a thread which is even more softer, you see these things that they call sea turns and snake turns and so on. The difference of this from our simulations is that in our case, the thread is vertically, we start vertically, and we keep changing the strain so that the thread is not able to adjust to one point. These kind of things you could call transient chaos, but at late times, it is just a constant. Here is another much more recent paper where they have a flow which becomes compressed. So it's a compressional flow and then expands. And they have a long thread in this flow. And here is a thread that can buckle even in 3 dimensions. And you can see a buckling which is helical. So the helical symmetry of the problem is also broken, can also be broken. We don't see this because we haven't introduced torsion in our problem. Although we solve equations in 3D, our problem is actually stays completely in 2D. To summarize everything again, so the main result is that the curvature as a function of arc length is a random function in space-time. Now this is turbulence. This is not a small dimensional system. This is a large dimensional system. There are hopes of analytic attacks because the local viscosity also gives chaotic solutions. And in terms of curvature as a function of arc length, which are called the intrinsic coordinate of the system, the equations can be mapped into nonlinear Schrodinger equations, except the external flow. So we don't really know how to solve this Schrodinger equation with external flow added to it, but that's what we are working on at the moment. So here is the paper in the archive where you can find all of this described in greater detail, which will make you thoroughly bored of it. Thank you.
Okay, thanks, Dhruva, for exciting talk. So we appreciate your time and your talk. Okay, so we take questions. Alan, yes.
Sir, I have this viscosity is too large for ensuring that the Reynolds number is very small. But I have this question that is this viscosity constant with respect to the strain? Because we are putting the filament, which is assumed to be made up of small balls. So when these balls are moving in the fluid, so in that sense, is this viscosity assumed to be constant, or is it?
So are you thinking something like Einstein's solution that when you put small balls in a fluid, the viscosity of the fluid changes? Is that what you are thinking about?
No, I'm not thinking in that line. Okay.
So what we are doing is, you see, we are using the Stokes equation, and we are essentially solving the Stokes flow with n number of balls which are connected to each other. And this, just we are solving it using what is called boundary integral method, which is exactly the range function that we use. There is a feedback somewhere which...
So my thing is, it's similar to what the first question I asked. So when there is a basically point fluid, with Taylor's first experiment we showed, there is no stretching, there's no shear, in fact, like the one you are applying for Euler buckling. So that comes back. But as soon as you put a thread, then it is like, by the way, so there's a thread, then it is experiencing some kind of periodic forcing. So in fact, it's a nonlinear.
The flow is experiencing periodic forcing, indeed.
The thread is experiencing a periodic forcing
through the flow,
and it's elastic and it's nonlinear. I agree with that, and that leads to your system. So that's my interpretation. To contrast with, I'm sure you probably you know it, but I just wanted to comment it. That Taylor's that blob does not experience it, or actually, if you zoom in the blob, I think that should also be experiencing some kind of distortion, but it is too
Mahendra.
tiny for it. Yeah.
Mahendra, have a look at this.
There are two concentric cylinders.
I will go ahead a little bit.
Can be moved by turning the inner cylinder with this handle. The annulus between them is.
So you see here, this is not a point. This is a square.
It is stretched around the annulus.
And it is stretched.
Yes.
Right? But it will come back.
But if you make a large enough square, it won't come back.
No,
now
why not?
Cylinder is turned back, attracted to its starting position.
The different points of the square will experience different stress.
As it does here also, right? Different points of the square experiences different forces.
But his thread, let's see his thread. Is it bigger than
it is bigger, but that doesn't matter.
Motion, the boundary of the fluid
bigger matters.
Determined at each instant by the motion
well,
of the
anyway, that's
wall.
my guess. Okay, I mean, I may be wrong.
By
the way,
in one way, the length does matter because the dimensionless parameter we use has the length.
Yes.
Right. But this is not the length. This is the length and the elasticity put together. So in this apparatus, say that if the thread is too long, it will start seeing the boundary of the apparatus. Right.
But look, in the square, the 2 points of the squares, the inner edge and outer edge, will see different shear, right?
Yes, right.
So there should be some time asymmetry should be reflected in that itself.
They see different shears and they move differently with time. But once you reverse time, they come back to exactly the same place.
The fluid.
You try to analyze it by simulation, the same simulation which you're doing right now. I believe it won't. I don't know. That's my guess. Okay. I mean,
but you see this, right?
But he's doing only once. He's doing once. He should do it several times.
Well, he does it later with a different thing.
I see.
Have a look at the movie later.
I will. By the way, so I heard one talk earlier by Otino. Have you heard of this? There's a book by Otino.
I know the book, but I haven't actually read it.
So that book, he made a very clear statement that in viscous flow, like what, in fact, the same flow he was doing it, the kinematics of the flow is nonlinear, though the background flow is linear because the particles are moving. But particle is moving in different velocities at different time. So if you, in fact, you fix the particle and look at, well, you can do the other way around. In the particle frame, it is experiencing different forces at different times. Well, he didn't say it, but I'm trying to just think like that. And so that can show chaos. And this is, in fact, showing us that it is time irreversible.
If you have many balls which are not connected, that is true, because that is one of the experiments that I told you about, where they have many colloids in the flow and non-linear because of colloid interaction.
Right.
You could say the same thing is there in our problem because of the bead interaction.
Right.
But in the second part of the problem, we actually threw away that interaction and only had the elastic nonlinearity, and it was nonlinear. In the first part, you are right. Both the nonlinearities are there, and it is very difficult to disentangle which is contributing what.
Okay.
Right. In the second part, that's why we actually remove one of them and see that it is still nonlinear. But the second part, the problem is not really that physical. Because when the two bits come close to each other, then this non-local problem will be there in the actual problem.
Okay.
You are right. There is a nonlinear interaction between beads here. And
actually, I'm not even, in fact, in that book by Otino, the talk I had heard, I saw that, read the book slightly. you do not need in a thread. In fact, I think it just does some particle simulations in that flow, and it shows that it is not time reversal symmetric or something of that sort. I don't remember that one. The book you have to refer to it.
I will look it up.
Yeah. Anyway, so Rodian has a question. So Rodian,
Yes.
please.
Please.
Okay. Yes. Thank you. Thank you for your talk. To me, it was a perfect demonstration of how the classical method of theory of turbulence can be applied for non-classical problem, non-typical problem with the chaotic behavior and so on. But in principle, I have some objection about what you put in the title, like postmodern turbulence. To me, I would say it is a pre-modern turbulence, by the way. But okay, maybe it is a philosophical discussion. Could you explain me? Sorry for my probably stupid question. If you come back to the slide with the gradient method, how do you solve the solution numerically with the gradient?
Right. I don't think I described it in detail here. I was.
No, with the previous the slide you mentioned that you took. Yes, here. Do you need that function f will be monotonic necessary or not?
Not in Newton's method, right? See, here the function could go up and down. It could also have more than one root. And then which root you find out depends on your initial condition, in your initial guess.
But sorry, if it is not, okay, imagine one root, but there is a local minima. Then you, at some point, you will find, for example, zero gradient. Gradient will be zero.
Yes. So
what
then
you will do?
Then, okay, I see what you mean. Then you may not be able to move at all.
Yes, this is my my question. So
you may not be able to move at all. So that kind of things normally doesn't happen in so large dimensions. But that basically means you are unlucky. You should start with another guess.
Oh, but again, so it was if to me, okay, in linear with the linear equations or maybe quadratic, you may avoid, but I don't see that it is to me this function must be monotonic in sense of in order you have in order the procedure will converge, because I can also give you an example when you will jump between two solutions periodically and procedure will not converge.
Well, absolutely, that can happen, but that's a perfectly valid thing. You see, if that happens, then I have a two-period solution. See, it can happen, for example, in the logistic map, right? Then that basically means instead of finding a fixed point, I have found a periodic orbit.
Okay.
Right.
But how do you avoid this deadlock? I would say, if I understand, your recipe is just to take another initial. If you find the procedure is not converged, then you just take another guess, right?
Let me show you this one. So if you look at this, or the thing before that, at a minima, your df dx will be 0. Right? So that basically means your delta x you will not be able to determine.
Yes. Okay. Yes, of course.
That is the main problem. We don't really face that. We have never actually come across that. But this is the usual problem of using Newton's method to find out the roots of any nonlinear equation.
Okay,
right?
so it is just not your case, I would say. Maybe your function.
Just to make sure that we are talking about the same thing, we are not trying to find minima of some function. We are trying to find zero crossings.
Of course, yes.
Right. So yes, but there are similar things you can use to also look for minimas. And then you can ask questions about, can I get stuck in a local minima, or I am looking for a global minima and things like that.
No, for example, with the half, I don't know how it is in English, half division method. So with the half division method, you always converge to the solution, at least to one solution. But as I told you that in case of local minima, suddenly you can stuck.
You are absolutely right. But think about using the half division method in 1D. Okay. Then you are in one point, you go to another point, and you find if the thing has changed sign or not. If it hasn't changed sign, there are no roots in between. You take a bigger step. Right?
Yes,
that's how the half division works.
Yes, yes.
But think about doing it in a very large dimension.
Oh, yes, yes. I understand. Okay, now I understand your point. Yes,
yeah,
it is even. Okay.
It's very difficult to limit the solution. Which way are you going?
All right. Yes, it is difficult to find a way. Okay, so basically, thank you. Yes, I understand why do you choose this method, and maybe your last slide. Let's speak about physics. So because at some point you put this question mark. Is it physics? Is it physics or not? But also here, yes. No. Please, last slide. You say this is turbulence, not a chaos as a system of an infinite dimension. What do you mean, not a chaos of the system?
No, I mean, okay. I think I am missing a comma here. I am saying this is turbulence, not chaos, as the system is infinite dimensional. You could also say this is a spatio-temporal chaos. See, typically when we talk about chaos, we talk about systems with low dimensions, like Lorentz attractor. But what I wanted to emphasize was that this is a large dimensional system.
Okay.
Because the quantity here is kappa as a function of S, and S has continuous values between 0 to 1.
Yes, then I understand you correctly. So this is not again the physical argument. So again, maybe for students it is also well known, but behind the theory of turbulence, the physics of fluids is a very important part. Is the ideas about energy cascades, about cascades at all.
Yes.
Conservative quantity and so on. So when you went through your last slides with the phase complexities, shape complexities and so on, is it possible to introduce some characteristics which will be conservative, which will characterize this buckling or shape complexity? Yes.
We have thought about it, but I haven't come up with something. And that's if we could have some idea, then we could borrow Kolmogorov into this problem, and then construct scaling solutions and so on.
This is not necessarily Kolmogorov, I agree. But anyway, then with this instrument, it would be easier to find difference between two-dimensional, three-dimensional results. But now it is hard to think. So I can imagine only this really exciting and also how to say puzzling problem, but difficult to catch with the physical arguments. So this is my.
I am also stuck, and I think my best approach is to go through the nonlinear Schrodinger equation.
Okay.
Because there is a mapping which maps this problem to the nonlinear Schrodinger equation. If you're basically in the nonlinear Schrodinger equation, you have a complex field, right? And the curvature becomes the amplitude of that, and the torsion becomes the phase.
Yes.
This is a mapping that is known from, I don't know who invented it, but this is known for at least quite a long time, that there is a mapping that takes the equations of Euler buckling to nonlinear Schrodinger equation. So my best guess is that that's the best route for us. But if I go completely to intrinsic coordinate, it's not very clear to me how to keep the external flow in the problem. Because the external flow depends on how this filament is placed in 2D. You see what I mean, right?
Yes, I see.
I can kind of try to write a theory, from nonlinear Schrodinger equation, I can try to write, there is some Lagrangian in this problem, or some Hamiltonian in 1D space, some Hamiltonian which is only function of S, right? And try to write a field theory and do Feynman diagrams and so on.
Yes.
But I can't do that because, at least I haven't figured out how, because this thing is also embedded in 2D, and the embedding matters because the embedding tells you what the flow is.
Okay. Yeah,
Because the flow is in background 2D. Right?
Yeah,
So
understand.
how
You are constrained by this this two-dimensional. Yes.
the embedding matters, and that's why I haven't been able to figure out how to go.
Okay.
I will not.
Thank
I
you.
think that's a forcing. The fluid is a forcing parameter. That's what I was trying to say in the beginning. It's not a
The fluid-
constraint. I would say is a providing the force for this. Okay. Now, by the way, I again the second, like what Rudin is telling, a system being infinite dimensional does not necessarily mean it's turbulent. Okay. Now, one criteria which I think is people also use it. I argued at one point that for instability, well, for convection near threshold, near instability, okay, when we have root to chaos, the spectrum is exponential, not power law.
Hmm.
So that we call it essentially low dimensional, where they do show this root to chaos.
I agree with you. To show that it is turbulence, we need a spectrum. That's a power law.
Yes, right. Yeah.
Absolutely. I agree with you. And we did try to calculate a spectrum. But the trouble is that I don't have enough good data to say that whether it's a power law or not.
I see. Okay.
So if I could, I would have been more bold in saying yes. And I agree with you. Absolutely. The difference between turbulence and something else would be that if there were power laws in spectrum, and that would mean scale invariance in some way. And yes, that would be really turbulent. I completely agree with you.
Good point, Mahendra. Yes.
Yeah. Okay, so at this point, I think we can stop. There's no more questions. We again thank Dhruva.
Thanks very much for inviting me. And I hope I will see you in person sometime this year.